Okay, Math 150, let's take another look at graphing a rational function. This time we're going to be dealing with f of x equals the function here, x squared minus 4x minus 5 in the numerator, and then over 2x squared minus x minus 3 in the denominator. So the steps are always the same. So the first thing I would encourage you to do is just go crazy factoring everything. Try to factor this guy as much as possible. It's going to save you time later on. When we factor the numerator on this one, we're going to get x minus 5. We're going to get x plus 1. When we factor the denominator on this one, you might try a couple of different ways to factor this one. I'm just going to go and do a little bit of guess and check. And I think we're going to need a 2x and an x. I also think we're going to need a 3 and a 1. So I'm going to put the 3 there and the 1 there. And then I'm going to need a negative x. So I think this is going to work out okay. So let me just double check this real quick. I'm going to get 2x squared. I'm going to get plus 2x. I'm going to get minus 3x. So plus 2x minus 3x gives me that negative x. And I'm going to get that negative 3. So I think we're in pretty good shape on this. So once it's factored, these are the steps. Step 1, find that domain. The domain is always going to come from the denominator. Our domain here is going to be where 2x minus 3 times x plus 1 equals 0. That's going to give us x equals 3 halves in the first one. It's going to give us x equals negative 1 in the second one. So x cannot equal 3 halves. X cannot equal negative 1. If you want to go with some interval notation on this, which is perfectly okay, you would be saying from negative infinity to negative 1. Then you're going to have a union from negative 1 to 3 halves, and then a union from 3 halves to infinity. So that would be the answer for the domain. I'll just slide that under there. Okay, so I hope that is making sense to everyone. Next up, we're going to be looking for the y-intercepts. So to find the y-intercept, I'm sorry, the x-intercepts. To find the x-intercepts, what we're going to do is we're going to set our function equal to 0. So here we go, x-intercepts. So we're going to do this function equal to 0, but that just means the numerator has to equal 0. Okay, so just the numerator has to equal 0. We've already factored it. We get x minus 5, and we get x plus 1. So our answers are x equals 5 for the first one, and now we get x equals negative 1 for the second one. But you got to be really careful on this one. What we've got is, in this problem, we have the same factor in the numerator as the denominator. That means that x equals negative 1 wants to be an x-intercept, but it also wants to be a bad thing. Well, here's the bottom line on this. Domain always wins, okay? If you've got a problem in your domain, that trumps everything. So this answer right here is not going to be an x-intercept because we already said that x can't equal negative 1. Now, some of you guys are going to say to me, can't we just cancel these two things? Can't we get rid of it? And algebraically, they're equivalent, but you lose the domain issue. And we always take the domain of the function that's the original function. This original function right here has a bad thing at negative 1. We can't make it disappear by doing algebra there. So again, the domain of the original problem always trumps everything else. So in this case, we've got an x-intercept just at x equals 5. So if I'm trying to draw this as we go along, if I'm trying to make a graph of this and just putting all of my information on the graph as we go along, what we're going to find out is right now we've got a bad thing at negative 1. So that's kind of an important point. We've got a bad thing at 3 halves. And we've got an x-intercept at 5. So for the first two, I'm just making the mark. For 5, I'm actually going to put the x-intercept in there. Okay. So next up is the y-intercept. And to find the y-intercept, we just substitute in 0 for x. We're going to do f of something. So when we plug in 0 on this one, we're going to get 0 squared minus 4 times 0 minus 5 in the numerator over 2 something squared minus something minus 3, putting our zeros in. We're going to end up with a negative 5 over 3, which is 5/3. So we know that we're going to have a a y-intercept of 5/3 right there. So from here, the next place we want to look is we want to look at the vertical asymptotes / holes. And those come from the domain problems. So now in this one, we were told that x can't equal negative 1. We were told that x can't equal 3 halves. Well, this is how you find out whether or not you've got a domain that's a vertical asymptote or a hole. We're going to actually now go back up here, and I want to work with the simplified version. So the simplified version of this is x minus 5 over 2x minus 3. So working with that, working with x minus 5 over 2x minus 3, I am now going to plug in the domain problems. So when I go to plug in the domain issues for x equals -1, what happens is I get -1 minus 5 over -2 minus 3. Again, I'm plugging -1 into x minus 5 and 2x minus 3. When I do that, I get -6 over -5, which is 6/5. If you get a number here, if you get a real number, in this case 6/5, this is a real number. That means we have a hole. We have a hole here. And the hole is located at the x value, -1, and the y value, 6/5. So if I were to show that, I would come back here and I would go -1, 6/5, which is going to be right here. So I'm just going to label that as -1, 6/5. And it's a hole because we got a real number. We got 6/5 out of that. Now, if we do the exact same process for x equals 3/2, x equals 3/2, well, this time I'm going to get 3/2 minus 5 on top, and I'm going to get 2 times 3/2 minus 3 on the bottom. That's going to turn into 0 on the bottom. This is actually going to be 10/2, 3/2, so we're going to end up with -7/2. But the point is, this is a number over 0. And that means we're going to have a vertical asymptote. This is going to be an infinite result. So as a vertical asymptote, we're going to come back up here to the 3/2, and we are going to draw a dotted line because our function is going to infinity or negative infinity there. Next up is the horizontal asymptotes. Okay, so for the horizontal asymptotes, I want to take my original function. So let me just copy this over. I want to take this original function, bring them down here. Okay, and we're going to ask the question, when I look at this, what is happening as x goes to infinity? What is happening as x goes to negative infinity? So I need to do it twice. So as x goes to infinity, well, this is where the degree of the denominator and the degree of the numerator matter. In this problem, the degrees are equal. I've got a square and a square. That means your answer is always going to be the ratio of those coefficients. So it's 1/2 because there is a 1 located right here, and there is a 2 located right there. Since the exponents are equal, get the ratio of the coefficients. We're going to see the exact same thing happen when we go to negative infinity, okay? The ratio of the coefficients. So we're going to end up with a horizontal asymptote at y equals 1/2. So we're going to come back up here, and at y equals 1/2, we're going to draw a horizontal asymptote. And I'm realizing I should have made myself a little more space on this one, so I apologize for that. I'm going to move my 6/5 up. Just move that guy up. Okay, there we go. That's at 1/2 right there. And my 5/3 is going to have to move up a little bit as well, just to be consistent. So let me put that up there, 5/3. Okay. So there's y equals 1/2. That is our horizontal asymptote. After the horizontal asymptote, the only thing that remains is your trichotomy number line. So we're going to make a trichotomy number line on this guy. So we're going to have, again, let's take that factored form. So I'll copy this guy. I want to use him again. So let's copy this and bring it down here. So I need to make a trichotomy number line. On the number line, you have to put all of your zeros and all of your undefineds. So we've got 5 for a 0 from the top. That was our x-intercept. We've got -1 as an undefined. We've got 3/2 as an undefined. I'm sorry, as an undefined. So now all we've got to do is use our test values and see what happens. So we're going to plug into x minus 5 over 2x minus 3. And we're also going to do the x plus 1. But to be honest with you, those are going to, they're going to cancel each other out, just like they did when we simplified. So we can use the simplified version on this one. So when we plug in, we're going to pick a number over here. So I'm going to pick negative 10. When I plug that in, this factor right here is going to be negative. When I plug in negative 10, this is going to be negative, this is going to be negative, and this is going to be negative. So we've got 4 negatives. That's going to make negative 10 turn out to be a positive result. Okay. Now I'm going to go and I'm going to plug in, this time, I'm going to plug in 0 because 0 is between negative 1 and 3/2. So when I plug in 0, this one's going to be negative, this one's going to be positive, this one's going to be positive, this one's going to be negative. So we're going to get 2 negatives, which is going to give us a positive result. So this is going to be positive. Okay. I'm going to choose another value to plug in. This time between 3/2 and 5, I'm just going to choose 4. When I plug 4 in, this guy will be negative, this one will be positive, this guy will be positive, and this guy will be positive. So I've got 1 negative in this situation, makes that guy overall negative. And then last but not least, I'll pick something bigger than 5. I'll pick something like 1,000. And I'll plug in 1,000. And when I plug in 1,000 for this one, this guy will be positive, this guy will be positive, so will he, and so will he. So we're going to get positives all the way around. Remember what that means? These guys mean we are above the x-axis. The negative means we are below the x-axis. And the positive means we are above the x-axis again. So I've got to go up here, I've got to connect my dots. I want to work from negative infinity until negative 1. I've got to stay above the x-axis, and I've got to use my asymptotes. Now remember, we said there was going to be a hole there, so it's going to have to approach that value, because that literally just erases 1 value from my graph. I stay above the x-axis, I go through the hole, that's what we're going to get. So now in the next region, again, this region right here until 3/2, we are above the x-axis again. So what's going to happen in this one, and I'm going to need to give myself a little more space, my asymptote's going to go all the way up. I am going to head straight to that y-intercept, and I am going to keep going up and approaching that asymptote like this. So that's what we're going to get for this particular section of the graph. Next up, we're going to look between 3/2 and 5. That tells us from here to here, we are below the axis. So I got to hit this point right here, and I got to start below the axis. I'm going to use this asymptote from below and hit that 5 like that. And in the last region, from 5 to infinity, I am above the x-axis. So that's going to mean head towards that asymptote, go above the axis, and kind of level out at that 1/2. So that is going to be the final graph for this one. Okay. So I hope that makes sense. Feel free to pause as you go along, look at the steps. Email me, contact me if you have any questions. I'll be doing 3 more of these examples and posting them over the weekend so you can keep looking at different rational functions and what happens. The bottom line on this one is the whole. Make sure you understand the whole. I'll do another example of that in one of the future problems. Hope you guys are having a great day. We'll talk to you all soon.